So if we start with just a polar pi bond, let's just look at a general carbonyl. What chemistry do we see? What stands out?
The carbon, the partial positive on carbon.
Okay. So hopefully you would see a partial positive on our carbon. And if we had a partial positive on the carbon, it became partially positive because the oxygen took electrons away. So we could envision some of the chemistry starting with this by looking at a resonance structure, right? And this is mostly what the first unit or the first chapter of this unit was talking about, is just looking at that reactivity. So if we're evaluating that, what chemistry would we then associate with this particular molecule? Okay, so we're hearing a lot of different terms get floated out there, so let's walk through that. If you're seeing nucleophile character, where are you referencing nucleophile character? Okay, the oxygen has that negative charge, so we might go through and call that a nucleophile. What other chemistry do we see? Okay, we see electrophile character because we have that positive carbon. What other chemistry do we see? What's that again?
Acid.
Where do you see the acid?
Well, it can bear the oxygen. So,
Okay, so you're not wrong by saying acid, first off. Okay, but by saying acid, you're probably digging deeper than you intended to dig. Okay, which is fine. Okay, so let's take it a step away from the acid for the moment. Okay, what else other than an acid? Base. Okay, with the lone pair on our oxygen could act as a base. Okay, so those should be our primary characteristics. And I'm going to skip the acid for the moment, but you're absolutely right. Okay, so if we were now to consider the reactivity of that functional group, we've got lots of different chemistries. We could throw electrophiles at this. We could throw acids at this. We could throw nucleophiles at it. A whole bunch of different chemistries are possible. Okay? Our job now isn't what's possible, it's what's probable. Okay? So very slight differentiation in that language. What things are more likely to happen? So if we're looking at these two sets of chemistry, it's the negative oxygen versus the positive carbon. Which of those is potentially more reactive? Positive carbon, because? So we can make an argument that oxygen wants to hold on to electrons. It's electronegative, so it could hold the electrons that way. That's reasonable. I would argue you should be able to come up with a better reason. Why would a positive carbon be less stable than a negative oxygen? They're both equally charged.
It's a secondary carbocation. Oh, it's surrounded by
Octets. See, 4 fingers? That's what that was. Wasn't trying to flash gangs. La Ocam Club. That carbon is missing its octet. That should be the biggest red flag that we need to fix. So when we look at the first unit, that's our primary focus. We are ending up reacting nucleophiles with that particular carbon. And the nucleophiles that we were reacting were all, in my language, stupid strong nucleophiles. Okay, so this was negative carbons and negative hydrogens. We didn't start by looking at negative oxygens, nitrogens, or even neutral oxygens and nitrogens. Okay? And we can't get neutral carbons and hydrogens acting as nucleophiles because they don't have a pair of electrons they can give up. Okay? So our primary focus is on these kind of stupid strong nucleophiles, our negative carbons and negative hydrogens. So this is where we got our hydrides from sodium borohydride, lithium aluminum hydride. This is where you got the Grignard, okay, popping in. That's where you got the Wittig reagent. Okay? And what you might notice is that we're starting to drop a lot of names, and those names that we're dropping are all on the carbon nucleophiles. Carbon nucleophiles are not easy to make, so almost all of them are named reactions. Right? As far as exams, I want you to be able to recognize both. I'll give you a name and structures. Right? So if you're just going to memorize names, that's fine. You can use that to leverage through an exam. Realize ACS is kind of a blend. Sometimes they give you both. Sometimes they just give you names. Okay? If they give you just names, I'll give you structures. Kind of makes sense? Yeah. So that was whatever that was, chapter 18. Okay, all of our stupid strong nucleophiles. And then what we move into is the next chapter where we say, okay, well, what about other nucleophiles like oxygen? Because oxygen has a pair of electrons. Couldn't oxygen act as a nucleophile and share electrons? Yes. Okay? But as we bring in that oxygen is with that negative charge, we should note again, or go through that same process that we went through with our carbonyl, what chemistries are available to us. We should be thinking the same thing for the hydroxide. What chemistries are available to us if we bring in hydroxide? That's our nucleophile and base chemistry. Okay? Before we start the nucleophile chemistry, okay, we would typically talk about the base chemistry. And in fact, that base chemistry was something we talked about all the way back in OChem 1, as far as my class went. Okay, what was that? Chapter 7. Okay? Don't stress about the chapter reference. Okay? So let's address that first before we start talking about the nucleophile chemistry, and that goes back to looking at our carbonyl, or looking at our functional group, our ketone, in this particular case. If that hydroxide is going to act as a base, it would have to react with an acidic hydrogen. Do we see any hydrogens that are clearly acidic? Okay, and depending on what you've been visualizing, maybe you do see them, maybe you don't. Okay, I would argue nobody should see them because there aren't any clearly identified hydrogens. Right? But if we take a little bit less of an explicit stance, or make it more explicit, we could acknowledge that there are hydrogens at the alpha position to the carbonyl. So our carbonyl is our primary functional group. That alpha position, one carbon off of that carbonyl, has hydrogens. And our initial assessment would be that those are not acidic because that's a carbon connected to a hydrogen. That's a nonpolar covalent bond. That shouldn't be acidic. Right? We can start with that as a blanket statement, particularly when we consider OChem 1. When we move into OChem 2, we actually need to start propagating our way through these channels and be like, well, why is it not acidic? And so what we would actually try and do is take that route where our hydroxide is acting as a base. I won't draw the curved arrow because there's a bunch of stuff already in the way. And if we remove that pair of that hydrogen, we would get a negative charge on that carbon. That negative charge is what we're signaling is no, we can't do that. That's not stable. Okay? And ultimately what we're referencing when we're saying that's not stable is we're comparing that negative carbon to what? That's an eraser. We're comparing that negative carbon to the negative oxygen. Where did it go? That's what we're comparing. Oxygen is a more stable negative, therefore that reaction shouldn't happen. Okay? And ultimately, we aren't saying that shouldn't happen. What we're actually saying is that this is an equilibrium reaction that heavily favors the reactants. That's our argument. In OChem 1, we just kind of sidestepped that whole equilibrium conversation and said it's not a problem, we don't worry about it. It just happens. Okay? It either goes forward or it doesn't. OChem 2, everything's in equilibrium. You have to have that consideration within it. Right? Before we get too excited about saying, oh, okay, well then it shouldn't happen, or it's in an equilibrium that favors the reactants, we have to go beyond just looking at the charge. Because what could that charge potentially do?
Is it nucleophile or?
Ooh, it could act as a nucleophile, true. Right? But what you're now saying is that it can continue on to do a chemical reaction. The only reason it can continue on to do a chemical reaction is because the equilibrium has some favoring for this product. And right now, we just established negative oxygen versus negative carbon. There's not a favoring for this product. So it's not going to act as a nucleophile because I'm not going to form it in any concentration that's valuable enough to run. So what else should I be looking for before I try to make it chemically react? Can I stabilize it? And hopefully what we would see is that we have a resonance structure. And when we go through and look at that resonance structure, that's going to change some of our interpretation. Okay? So now when we go through to evaluate and we want to compare our product back to our reactant hydroxide, which of those two structures should I be using to make that comparison? Both is a fair answer, but pick one. The more stable one. Which one's the more stable? The negative oxygen. So this is where we're getting that best versus useful delineation. Okay? And now when I make that comparison, negative oxygen versus negative oxygen, is this actually a fairly legitimate equilibrium? Yes. Because it is a legitimate equilibrium, now I can have that conversation. Could this structure now act in another chemical reaction? Could it go through and do some nucleophile chemistry? Yes. Okay? But I have to prove that that product that I've made, that intermediate in my mechanism, is valid. Okay? There's a reason for it to exist. Between those two structures, which one should I be using to advance in my chemical reaction? The negative carbon, because the negative carbon belongs to our useful structure. And so if we're talking about the nucleophilicity of this structure now, it's that negative carbon, not the negative oxygen. Could the oxygen still act as a nucleophile? Yes, it can. Okay? The circumstances that force the oxygen or increase the odds of the oxygen reacting as a nucleophile become trickier to manipulate. The primary chemistry is going to be on that nucleophilic carbon. Kind of make sense?
Can you repeat that? Why is the carbon?
Between those two, why did we call best? Why did we call the negative oxygen structure better than the negative carbon structure? Say it again. Oxygen can hold on to the charge better. If it holds on to the charge better, is it going to act as a nucleophile? What does the nucleophile have to do? It has to donate the electrons. So if the oxygen is going to hold on to the charge, you've already created an environment in which it should not. Right? So we've looked at our stupid nucleophiles coming in and attacking, doing a direct addition to our carbonyl. Right? We could then go through and say, well, what are some other nucleophiles? We could bring in the oxygen, and our default oxygen is going to be hydroxide. That default hydroxide immediately brings up the acid-base chemistry that we should be aware of. Okay? But we also have this nucleophile chemistry. That nucleophile chemistry is our acetal chemistry. I kind of want curved arrows for this, but I think I can get away with it. Our negative oxygen can come in and attack. Yeah? So nucleophile attack. The oxygen comes in, attacks the carbonyl. That's all we're saying comes out of this. Is everybody okay with that? Yeah? Okay. What functional group do we have? Okay, so we're getting a lot of people saying carboxylic acid, so let's draw up a carboxylic acid. So the carboxylic acid has the OH, yep, we've got that. It's got the carbon, yep, we've got that. It's got a second oxygen, yes, we have that. it has a pi bond between the second oxygen and carbon. Do we have that pi bond? No. So it's not a carboxylic acid. Getting too close. Okay, we might go, oh, it's an alcohol. Okay, it's not an alcohol. And it's not an alcohol because that green oxygen and that black oxygen directly interact with each other. What do we mean by that directly interacting? Well, what are they both connected to? That carbon. Okay? Because they're both electronegative, they're both withdrawing electrons from that carbon, which means that carbon starts to become positive, so what does it start trying to do? Pull electrons towards it. But if it pulls those electrons in, what happens? It has to boot out the other one. Okay? Or it pulls them in from here and tries to boot out that. Okay? Which means those two oxygens have a direct connection with each other. They are affecting each other's chemistry. This is a new functional group now. Okay? The name of that new functional group, depending on how specific you want to get, is going to come to different levels or extents. Okay? I place it in the acetal chemistry. Okay? It is not officially an acetal, okay? And it's not formally a functional group yet. To actually hit that final functional group, we would have to neutralize it. How could we neutralize that? Someone say it. We can add an acid. And all we're doing is protonating, right? Okay. That neutral structure is where we could now have a conversation about what that functional group is called. Okay. That identity of that functional group is really tied, in my mind, to that carbon. That carbon is the primary chemistry on it, and that's where I would call it in the acetal family. Okay. The definition of an acetal has a little bit more context behind it. Right? We already had one of your classmates start to say hemi because they were starting to reference the hemiacetal because it has characteristics of what a hemiacetal would look like as well. Formally, okay, this is not an acetal or a hemiacetal. It's what's known as a hydrate. Okay, but again, the chemistry is ultimately all the same. So these are all kind of in the same kind of category or group. That chemistry is again centered on that red carbon or that red dot. Before we get through to that neutral structure, we want to have a larger conversation about that first step. Okay, can I erase a whole bunch of stuff? So that when I say first step, we aren't getting confused by everything else that's on the screen. Okay, so I'm going to get rid of all of that. So our first step, that red arrow, just like we addressed with the acid-base characteristics of the carbonyl functional group, is this unidirectional? Well, we just started it off with none of our chemical reactions are unidirectional anymore. So it's going to go back and forth. The question is now, to what extent? Right, so if you go through and look at that, what are you going to compare on each side of the equation to decide which side is favored? And again, remember, it is only this red arrow that we care about. Okay, if we make it a little bit straighter, we could just say here. Should I favor products or should I favor reactants? How would you decide? Stability, cool. Stability of what?
Like the charges?
Yeah. You'd look at the reactant side and the product side and you would say, where do I see stability differences? So when I look at the reactant side, my primary focus is going to be the hydroxide because it is the charged one. When I look to the product side, what am I looking at?
The positive,
Okay, positive hydrogen. Cool. Where's the positive hydrogen? Clarify for me. Where's the positive hydrogen? You said O.
Uh,
It's in the second step. I don't care about the positive hydrogen yet. Okay? Because is it being the second step, I still have to prove that the first step happens. If the first step doesn't happen, I don't care what happens in the second step.
so the negative oxygen.
Cool, the negative oxygen. Okay, so if we're going to now go through and compare, this is going to become relevant here in a second. Okay, we only have one product in this reaction. It was a direct addition. There's only one product that comes out, and I'm looking at a negative oxygen. So if I make a comparison now between my reactants and my products, charge, they're both charged. What's the next thing? Size. What is the atom in each case that's negatively charged? Oxygen. Okay, is there a size difference?
No.
Is there an electronegativity difference?
No.
Is there resonance?
There's no resonance in both.
There's no resonance in both. Okay, do we get an inductive effect? Yeah, we kind of get an inductive effect coming into that. Okay, that's real low on our totem pole, but you know, if we had to force, yeah, sure, okay, we get a little bit of an inductive effect, which ultimately says, what's the difference in stability?
Wait, the right is favored more because there's
By a tiny, tiny fraction. Okay, and if we're looking at tiny, tiny fractions, are we looking at making much of that product?
No.
No. Okay, we've defined tiny, tiny fractions before, but ultimately in ranking, which one of these structures is more acidic, not which of these reactions is more probable to happen. Okay, so we're now changing the kind of story behind this. That difference is now very nuanced. I drew in 2 boxes, technically 3 boxes. What are those boxes about? And if it helps, I can redraw this a little bit. So right now, we're saying top line is slightly longer, right, than the bottom line. And I have 1 box, and I have 2 boxes. This is painful. You're trying to pull back some hardcore memories on this. Is that just because you watched the lecture, or did you just happen to remember that? Oh, that's no fun.
What's the arrow?
Okay, what we're pulling back is entropy. The difference in energy between our reactant and product is so small now. Okay, effectively, our delta H is a tiny ass number that when I consider the energetics for the overall reaction, delta G equals delta H minus T delta, you remember all that fun stuff? This number is so small that the spontaneity of this reaction is now being controlled by delta S, our entropy. Right? And if we look at entropy, what is entropy always doing in a spontaneous system? Not you, Lorraine, because you watched the video. Did you watch the video?
Yeah. But I knew that anyway, but yeah.
Then not you either. If we think back 152, what is entropy doing spontaneously? What is entropy? Okay? And this is where we're going to get a whole bunch of different definitions, and I personally hate probably all the definitions that you were taught, which is fine. Okay, we get disorder. Well, what the hell is disorder? Right? Something. Yeah. What is entropy? It's a measure of possible motion. That's it. So when we say disorder, it always gets more disordered. What are we saying? There's more motion associated with that state. So if you looked at a room over time, it gets disordered because everything is occupying different spaces. It's not confined to one space. Progressively, all those things are moving across, and it becomes a messier room. Right? And that's why we like to use disorder as that reference, but it's ultimately just motion. You're saying there's more possible states where those things can exist. Right? So you can look at things called microstates if you really want to, which is a really confusing, nasty, and you just made a face. They talking about microstates in chemical engineering? Yeah. Okay. Yeah, they talk about it all the time because it's the more precise way of evaluating it. Okay? We don't need to get precise. There are approximations that we could make that you made in your Chem 152 class. And the first place to start, how many objects? More objects means more entropy. So if we're looking at this reaction progressing forward, what's happening to our entropy? It's decreasing. Is that a favorable system? Nope. So this balance between the enthalpy and our entropy shifts. What we're now defining is effectively a line. And by defining, we're really just hand-waving, making it up and saying there is a line here. Ta-da, it just happened. But we don't quantify it because organic chemists don't like math. This organic chemist doesn't like math. Okay? And ultimately what that's going to do is overwhelm that inductive effect to the point where the reverse reaction now dominates. Okay? So that when we're looking at this chemical reaction, it effectively says, doesn't happen. Right? And we've encountered this. Where did we encounter it? We've encountered it in lab. Let me erase all that stuff because nobody cares about boxes and delta G's and all that. In lab, we encountered it with if we get a little bit more precise. Right, more or less? Oof, probably more on the less side of that. Let's fix that. Does this look familiar for those people in lab? What are we drawing? Yeah, this is the dye molecule. Okay, and what happens? Okay, that's what happened. That structure wasn't stable. Okay, and it fell apart. Okay, before we fall it apart, pretend that made sense. What's special about that red carbon? And if you're trying to figure that out, look at the red carbon that we just identified and look at the carbon in the upper right-hand corner.
There's 2 oxygens pulling on it.
You've got 2 oxygens pulling on it. What we've just drawn in this structure from our lab is effectively the same thing that we're getting up there when we're talking about our hydrates. That structure is unstable and it wants to fall apart. Okay? How does it want to fall apart? It wants to revert back to the carbonyl. So if we go all the way up to our hydrate, ta-da, yay, we made it. What does it want to do? It wants to fall apart and come back to the carbonyl. Kind of? So when we're looking at this chemistry, it's a kind of a weird system to talk about because we spend this whole lecture about, oh, let's make this molecule, let's make this molecule, let's make it, let's make it, let's make it. And ultimately, the end of that lesson is
Make a small amount.
we don't make it. Okay? Well, if we don't make it, why have the conversation about them? That's a much harder question. So there's a couple things that could be tied to that. You just want to study chemistry, so we're going to look at reactions that don't happen very much. Okay? Most organic synthesis isn't about reactions that don't happen. What we're looking at is reactions that do happen. So why would I possibly want to do a reaction that does this chemistry? Yeah, I'm just going to erase all that. Why would I possibly want to do a reaction that does this? Is there a reason for that? Because if there isn't a reason, spoiler alert, we shouldn't frickin' study it. So there's got to be a reason. Why do I want to do this chemical reaction? Because if I know why this chemical reaction is useful, now I want to study the reaction and figure out how I can make it more likely to happen. Any ideas? You want a hint? The hint has to be with exactly what we started the entire lecture with. What is the chemistry you see within the carbonyl? What is the chemistry you see in the product? That's it. What was the chemistry of the carbonyl? It wasn't just everything. We saw everything there, yes, but what was its primary chemistry? It was that electrophilic carbon from the polar pi bond. Take a look at the product. Do you have a polar pi bond anymore? No. And so, well, but I still have an electrophilic carbon because there's two electronegative elements connected to it. How is the positive carbon in our reactant, our polar pi bond, reacting? What part of it is reacting? That's a real tough question, but you can do it. What part of that carbon is reacting? The what? I heard electrons. It's not electrons. What's the positive charge? It's the p orbital, which means my nucleophile is coming in from the top or the bottom of this structure. Are there electrons on the top or the bottom of this structure? This is all planar, which means those two spaces are entirely open to attack. If we look at the electrophilic carbon in our hydrate, where is it going to react? Backside. And what's on the backside of that OH leaving group? A whole bunch of electrons. Which means I don't get good nucleophile attack on that structure. I get great nucleophile attack on this structure. Right? So if I had a structure that had a carbonyl in it, I could convert that carbonyl into a different structure. And because I know that chemistry in particular was reversible, that's a little more dramatic when you don't use the eraser, reversible, I could convert it into that other structure. I could do some other goofy chemistry, and then I could revert back to the carbonyl. Right? What we just did is called create a protecting group. Right? So for instance, if we looked at a larger structure here, and we drew extra stuff. I don't know what extra stuff. Let's just draw some stuff. That was probably a bad thing to attach, but whatever. More stuff. If I wanted to do some chemistry out on this alcohol, but I knew that that carbonyl would get in the way, what I could do is first protect the carbonyl by converting it, getting rid of it, converting it into a different functional group that I know is reversible. Then I can go through, target the other functional group, and then I reverse back. That's a pretty powerful technique. Right? At least old school. Why is new school that technique a bad idea? And that becomes a little bit of a tougher question. So if I want to do a chemical reaction, first thing I'm going to do is, we'll pretend, convert that to a squiggly so that I can then add a circle, and then I can get to my final product where I have the circle and the line, right? So the goal is to do this. That's what I want to do. I just want to add a circle to my structure. But that line is going to somehow affect my ability to put the circle on it. So what do? I convert the line into a squiggle. Then I put the circle on. Then I get rid of the squiggle back to my line. Kind of make sense? Okay, so I have two pathways that I can talk about this. Okay, we'll call it the black pathway versus the red pathway. Which pathway do you think is better? Why is the red pathway better?
Because it's more sustainable, or like you're not using as much.
Okay, so we're getting all sorts of fancy with this. You don't have to get fancy. Yeah, there you go. 1 step versus 3 steps. I like red better, right? Your number one objective when you get into lab is to do what? Get out of lab. Okay? Ideally with all your fingers, toes, and appendages and things like that. Okay? So your goal is to make it out as quick as possible. So if we're looking at these two syntheses, black versus red is by far better. Okay? But what if red doesn't work? If red doesn't work, then I have to find another pathway. That other pathway could be that black pathway. Right? Why even then is it a bad idea to do that black one? What makes that black one not particularly good? Yes, it's longer, but what else?
Do you get high yield? You can make a lot.
So we can talk about yield. Yeah, let's say the yield is great.
You have a lot of extra like byproducts.
One of the things that we tend to neglect when we look at OChem is all the individual pieces along the way. Okay, those byproducts. We focus in on the primary structure. If I go through and look at that first step, what happens? I've also produced that line. That line is no longer useful to me. That gets thrown away. Okay, I then do the chemistry I want, so we won't worry about that one because that's going to be the same in both. And then my last step is I have to add the line. So I have to somehow bring that chemistry back in and produce a squiggle. So if we're looking at that top pathway, we're doing the overall chemistry that we want, but we have to add 2 kind of satellite chemical reactions to this. Those satellite chemical reactions are necessarily going to produce more waste. Okay? More waste is generally a bad idea. Okay? Because where does the waste go? Into the trash. Where does the trash go? Into the world. Okay, well, it goes into a dump. That's okay. We won't live in the dump area, which is patently false. All you've got to do is look back at history and you will find we build houses on dumps. Okay? We've built houses on radiation sites. Okay? That history gets lost over time. So what we want to try to do is change our focus and minimize that waste stream as much as humanly possible. Okay? So when we're trying to target a synthesis, this black process that we're talking about with our hydrates, acetals, hemiacetals, as a grand scheme is starting to fade out of the curriculum because that's a bad synthesis. So that's why we don't want to do it. Kind of makes sense? Okay? And instead of just calling it bad synthesis, this is where we come up with different names. Okay? And you heard some people dropping some names. It's more sustainable. Yes. Okay, you could hear green chemistry. Green chemistry is a hardcore philosophy that has 12 tenets. Some of those tenets ultimately say protecting groups, which we just addressed here, is a stupid idea. Stop being stupid and be smart. Figure out ways that if that red one doesn't work, you come up with an entirely different path. You come up with a blue path. So you change your approach to solving the problem. Instead of taking this easy, well, I know I can do it, we don't care that you can do it, you're producing waste and toxins. Limit that waste and toxins. Does that kind of make sense? Okay. So that's kind of one of the reasons where this functional group comes up to your initial question, Maureen. Does that kind of help?
I forgot my question.
You said just talk about acetals.
Oh, yeah.
Right? So you give me a lot of rope to run with however I wanted to talk about it. Okay? And the lecture video kind of goes through the details of each of the different steps, mechanisms, all of that fun stuff, and it adds in the extra characteristics of how hydrates, which is where we started, are different from acetals, are different from hemiacetals. And I will quickly draw those up while Andrew asks his question.
Oh, I was just call back to protecting group can have backside attacks from
The carbonyl versus the.
That is based off, you're talking about the lecture probably, a little bit.
You kind of like, I just forgot what you said. You said that,
Backside attack is very limited. So when we go through and look at all three of these functional groups,
yeah.
if we're going to look at how these would revert back to our carbonyl, so that's supposed to be one of those funky looking brackets. Got the funky part right.
Yeah.
Going back to our carbonyl, all three of those don't have successful backside attacks.
That makes them a weaker electrophile.
Yep. So they'd be poorer electrophiles, which is the whole point. The carbonyl isn't running backside attack, but it is directing a nucleophile attack. Okay? That nucleophile attack is reacting with the pi bond, which is now very accessible. A nucleophile with any of that acetal family doesn't really have backside attack. So to get them to react, you would have to do different things. Okay? You would have to activate them to force that chemistry to happen. Kind of make sense? So within these, if we look at, this is the hydrate. When the hydrate reverts back to the carbonyl, what you end up producing is, how do I color code this? Call that a hydrate. You'll get the carbonyl and you'll produce water. Because if you look at the carbonyl structure and our hydrate structure, what's the difference between them? Water. So we call it a hydrate because what did you do? You just added water to the molecule. That's it. Okay. The next one's known as a hemiacetal. And if I took the hemiacetal back to my carbonyl, what I will end up producing is the alcohol. And if I look at the final form, our full acetal, if I take the acetal all the way back to the carbonyl, right? Yeah, let's just say back to the carbonyl, I would get 2 alcohols. Okay? So what we're talking about is how those bonds get cleaved. Does that kind of make sense? Is that a yes? Okay. As we navigate, so I would argue we can split the hydrate entirely off. The hydrate isn't involving any alcohols. Right? It's still using oxygen as a nucleophile, and so ultimately, to me, all of the chemistry is the same. It's just oxygen's a nucleophile. Right? The hemiacetal and the acetal are slightly different because what's next to the oxygen isn't just hydrogens. I get another R group. That R group changes some of that chemistry. What does R stand for?
Carbon.
Ultimately, it stands for anything that's not going to change the functionality significantly, which usually means carbon. Okay? It can sometimes mean hydrogen. In this case, we're using it to exclusively mean carbon. What else do I need? So how do I get the acetal to become the carbonyl? Because if I go through and look at these pieces, right, I've got the carbon chain, 3 carbons, yeah. Right? I got 2 ORs. Yeah, that makes sense. What's missing? How do I get the acetal to become the carbonyl? Yeah, I need a pi bond. A pi bond between what 2 atoms? Carbon and oxygen. Do I have an oxygen up there if I cleave those ORs off? Nope, which means what do I need? I need another oxygen source. I would add water. Okay. When I add that water, okay, we can navigate through this mechanism. We don't technically have to add acids or bases, but what we'll find is we'll generate lots and lots of charges, okay, through that mechanism. Those charges are now higher energy states and are less likely to happen which is why when we're trying to do this conversion, we will almost always catalyze it. And we usually catalyze it with acidic conditions, but you can catalyze under basic conditions. Right? That acid can protonate one of our oxygens of our ORs, turn it into a great leaving group. Fantastic. Once it's a great leaving group, what could happen? It leaves, which would leave behind a positive carbon, also known as a carbocation. That carbocation with the p orbitals on both sides is now very easily accessible to the water as a nucleophile. Right? And as it does that, it would have charge on it. But what it's going to end up looking like is it's going to go from the acetal to the hemiacetal to then navigate to the full acetal. Okay? Kind of makes sense? Okay. So we just walked through kind of all the logistics behind it. There's a bunch of mechanistic detail within this. Okay? I think if you look at the mechanism, it's like 8 or 9 mechanistic steps. Of those 8 or 9 mechanistic steps, 2 of them are not acid bases. Okay? So the vast majority of it is just an acid-base mechanism. Okay? That you're just changing those charge states so that a leaving group can leave. Or that structure doesn't leave and it stays on. Okay? So if you want the detail of those mechanisms, I'm not going to draw it all out here. I'm going to tell you that you should watch the videos for that. Okay? But if we consider what we just went through, 45 minutes of look at this is what an acetal is, it can act as a protecting group, so yes, there's a reason that we can go through and do it, but why? We just said protecting groups were a horrible idea, right? So why spend all this time addressing all of this if all of it just sucks? Because you enjoy pain. That is why you all are here.
I have a question.
Go for it.
So before we were making the hydrate,
Yep.
so we need to add OH and an acid to the carbonyl?
Say again.
To
Make the hydrate.
We need to add an acid.
An acid catalyzes the reaction. It is not strictly necessary to run the reaction, but it speeds up the reaction. So that if we were going to try to ever make an acetal, okay, or even a hydrate, we would always have an acid or a base catalyst to help force that chemical reaction to happen. Because again, lots of protonation states, we're trying to force it to go the direction we want it to go. Kinda.
Neutralizes it?
It's ultimately not going to neutralize the acid because it's an acid catalyst.
Well, the
So
acid neutralizes, and then after we added the OH, we added the acid to neutralize it.
the acid catalyzes all of your reactions, both forwards and backwards. So maybe I would have to look specifically at what you've got written down to reference that. I may have to double back to that.
Okay.
What do we see here?
The sugar?
Is this some kind of sugar? Yeah. Where would we see sugars? In your next chemistry class, more than likely, like a biochem class. All right. Well, why would we care about sugars in this particular unit?
Got a lot of O's, H's.
Or hose, if you want to look at it the other way. Yeah. Why would that be particularly relevant? Why do we care about sugars?
Tastes good with energy.
What can you tell me about that red carbon? It's a red carbon.
I was gonna say that. It has two oxygens pulling on.
It has two oxygens on it. You mean, what do we have here as a functional group? It's not going to technically be a hydrate, but I like where you're going with that. Because if we're looking at a hydrate, we have the two oxygens on it, And we would have 2 hydrogens. Do we have 2 hydrogens? Not directly connected to it. So what do we have? We have a hemiacetal. Right? Carbohydrates are the simplest carbohydrates are hemiacetals. So why do we need to study it in OChem? So that when you see it in biochem, you can understand something about the chemistry there. Right? We say, oh, but these shouldn't happen. Biology has a nasty way of making things that shouldn't happen. Okay? Just look at us. We all exist, and what are the odds for us existing? Yeah, very, 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 very slim. And yet we're all here. Okay? So biological systems can force certain chemical reactions to happen and for certain reasons. Okay? When we looked back at the hydrates, the acetals, and the hemiacetals, how is my sugar that was supposed to be glucose, and I'm pretty sure it is totally not, different than the hydrate, hemiacetal, and acetal that I drew up on the left? How is it different? It's in a ring. And we look through the logistics of forming all of the hydrates, the hemiacetals, and the acetals, the likelihood of making those reactions energetically, tiny favoring. Entropy said, hell no. Okay? But when you lock it into a ring, as long as that ring is a 5 or 6 membered ring, it becomes more stable. I actually drew glucose?
Yeah.
Oh, wow, look at that. Isn't there supposed to be an oxygen there? Isn't that another oxygen?
It's a circle.
There shouldn't be any double bonds in straight chain,
Yeah.
not the cyclic form. Oh, no, that is just a hydrogen.
Yeah.
No, because I already have the oxygen. That would make it another hemiacetal. See? Can't teach an old dog new tricks. Okay? So that cyclic structure is one of the things that favors the formation of the acetal. So if we're going to go back to our protecting groups, we don't want to just add 2 alcohols. We want to make sure that when we go through to make that acetal, if we were going to do it as a protecting group, we want them connected. Okay? So synthetically, this is a protecting group. As a protecting group, this is bad chemistry. We don't like protecting groups. Okay? It's not very green. But if we were to do it, we want to make sure we do it correctly. Forming a cyclic protecting group is better than forming the kind of open chains. And we can leverage biology to help us with that. Okay, and now here's where I'll probably screw up chemistry here, because as Jody just pointed out, isn't there a double bond? No, not in the cyclic version of the carbohydrate. 1, 2, 3. Oh, I should just give up. I know I'm not going to get it right. The cyclic form of the carbohydrate is actually very, very, very stable. Right? Well, if it's very, very, very stable, how are we using it as energy? We don't. What does our body do? It reverts the cyclic structure to the straight chain. In the straight chain form, now it can do a bunch of chemistry. Okay? So when you move into biochem, you're going to talk about what enzymes are being used to navigate these cycles, to force it into the ring structure or to break it open. That's the point of those sections. Okay? And within that, they'll talk about all sorts of extra names. They'll start addressing what's happening at that carbon. That carbon is known as the anomeric carbon. Okay? Well, did you form it where the OH was down, or did you form it where the OH was up? Is there a difference? Yeah, One, they're diastereomers of each other. And since they're different, what do you have to be able to do? You got to be able to name them differently. So you'll hear alpha glucose versus beta glucose. You've got a bunch of stereocenters on there. Do you really want to label out all the R's and S's for every single one of those? No? So what do? They came up with a new nomenclature system. That new nomenclature system looks at the penultimate carbon. What? It looks at this carbon. And it says, where's the OH? Is it on the right-hand side? That's a D sugar. Right. I think I got that. And if it's on the left-hand side, it's an L sugar for dextrorotatory and levorotatory in slightly different systems. So if you remember D and L back when we talked about optical activity, similar system here, but these are capital D, capital L. Okay, why capital D and capital L? Because they're based off of the structure, not a physical observation. Okay, because nobody can see the actual molecules. We're looking at the drawing that we've put out. So they'll add a whole bunch of nomenclature systems to it that, in this person's opinion, are completely arbitrary and probably unnecessary. But that's what we have to work with. Kind of, sort of. How would that chemical reaction happen? Why do we care about the penultimate carbon? Why not talk about the pencil ultimate carbon? Right? Or the marker ultimate carbon? Why do they care about the penultimate carbon? Why do they care about that blue one and not the red one or the green one? Go louder.
It detaches the oxygen at that point.
The lone pairs on that oxygen are what came up and connected. They're what came up and connected to form technically our hemiacetal. It's that cyclic structure. That's why we want to know where that is, because if we know where that is, that dictates where our OH is going to come out on the other end. That's kind of neat. Okay? If you're into that biochemistry stuff. Okay? But that's arguably the primary reason we talk about acetal chemistry, is that it is critical importance when we talk about biochem. You're like, but I don't have to take biochem. That sucks for you. You're welcome. Kind of, sort of? I don't know what else I can say about acetals. Do you have questions? Are you regretting your question now? Ooh, you aren't even answering, so yeah, that's a yes. Okay. Acetals as a class, we're trying to understand what those structures are. That's everything on our left of this screen. That's the hydrates, hemiacetals, and acetals. Okay. Those can be or are all converted from carbonyls. Okay, that's following our nucleophile addition chemistry. It does chemistry that, generally speaking, we would kind of ignore. Like, it isn't all that particularly useful for us. We talk about it because it brings in the concept of protecting groups, and we talk about it because it brings in the concept of carbohydrates and sets you up to theoretically be better in biochemistry when you talk about your carbohydrate chemistry in biochem. That's why it's addressed. Okay? Within it, lots of mechanistic detail to watch out for. If you're running under acidic conditions, what charges should you see in virtually every mechanistic step?
Positive.
Positive. If you're running under basic conditions, what charges should you see? Negatives. Okay, so you can see questions on the ACS saying for this mechanistic step, or which of these is the most likely mechanistic step within the acetal hydrolysis. Okay, under acidic conditions, you're looking for those positive charges. So you're looking for those structures that match that mechanism. Kind of makes sense? Within it, the other common thing that they'll note is if we look at what I circled for the protecting group, and if you go back in the slides as well, right, if we drew out the carbonyl, that was probably the slowest way to erase everything. Which one of these oxygens gave me my carbonyl oxygen? Right, and I'll help out. We'll color code. Was it the red oxygen or was it the green oxygen to make my carbonyl?
Can they be two separate? I mean, those, wouldn't water come in later and then make the last?
Yeah. Yes, it was a rude question. Neither of them make the carbonyl. That carbonyl oxygen is coming from water. Okay. What happens on the other end? What's the product? Oops. Well, we have those two carbons. We would have our red oxygen and we would have our green oxygen. Those need to be, if we're looking at our neutral structures, alcohols. So if we're looking at this chemical reaction that can go backwards and forwards, if I want it to go towards products, what can I do, go towards the acetal, what can I do to make as much of that acetal as possible from my ketone? Same deal, 152, doesn't go away. What can I do to increase the yield of acetal?
Like more tones in?
Put in more water. Where's water in my reaction? Water's with my acetal. So if I put water on this side, what happens to my equilibrium?
We add more alcohol.
It goes the other way to the ketone. If I want more acetal, what do I want to do?
We add more alcohol.
I want to add more alcohol. Right? So what you end up doing is playing a game of Le Chatelier. And you got to pull up all of that, dredge up all that old content to go backwards and forwards between those. Okay? As it is, I'm showing it under neutral conditions. That's not particularly useful. So we would want to add an acid to catalyze that. But that acid catalyst does not favor reactant or product. It just gets us to equilibrium faster. So if I want to speed this reaction along, depending on the directionality that I want, I will add either more alcohol or I will add more water. Okay, what else could I do? Instead of adding, I could
Use.
reduce is an interesting word set. That's fine. Okay, I could lower the concentration of water. If I remove water from the reaction, what's going to happen? The equilibrium is going to shift to make that water. So if I ran this reaction, I put a lot of alcohol and the ketone in there, and I put it in with molecular sieves. Molecular sieves are a drying agent, tend to soak water out of the reaction. Right? If I do that, the water is produced and it's now immediately removed from the chemical reaction. Well, if it's removed, the equilibrium says, oh, I need to make more. So it will constantly try and make more of the acetal structure. If I want to reverse the reaction, what do I need to do? Add tons of water. I'm also going to produce this alcohol. Do I have anything that can remove the alcohol? That one gets harder. You could try and play around with boiling points. Right? The alcohol probably isn't going to boil. Right? That's the diol. That's going to have stronger intermolecular forces than our water. If you're going to add boiling, you're probably going to boil out the water. But what you might be able to boil out is the ketone. Right? Depending on your boiling points, you may be able to distill out the ketone. And if you remove the product from the reaction, you're going to shift to make more of those products. Make sense? So those are the types of questions that you'll get with your acetals. Right? You'll look at just being able to identify them. Do you see that carbon with your two oxygens connected to it? Right? Can you break it apart? Go back to your ketone and the alcohols? How do you favor one direction or another? Do you recognize the value of carbohydrates? Other questions? Y'all are way too depressed. Do I just suck the energy out of everybody? Sure feels like that. You're not supposed to say yes to that, Casey.
Sorry.
So, pattern recognition. We're trying to follow patterns that we've already seen. Our acetal, our hemiacetal, and our ketone. Right? Those three structures should be written in your notes because we've drawn them out 3 or 4 times already today. So what we're trying to do is find out where this structure is within that pattern. Right? Officially, we're cheating. We're starting from the location of knowing this is an acetal. Should you be able to identify this as an acetal quickly? Yes. Where's the acetalic carbon? It is the top carbon. That's the carbon of my acetal. So if I'm going to go through this process, what happens to the bonds between that carbon and the oxygens? What happens in the first step? What happens to the bond between the acetalic carbon and our oxygen?
It leaves.
It's gone,
Yeah.
right? In the second step, what happens to the other one?
It leaves.
It is also gone. So if I'm looking at that structure, the first thing that I would try to do would be, as much as possible, copy and paste that drawing. Oops. Which is challenging because of the shape of this little bugger. There's my acetalic carbon. If we consider what's transitioning, what happens to the bonds between the acetal carbon and the oxygens?
They break.
They go away. Done. So I can delete them. What happens to them at the end? I drew them as negatives. Right, but they shouldn't be negatives. What should they be? Positive is the wrong direction. Right direction, just too far. Okay, so let's come back to that. What happened with my water? Where did that oxygen go? It attached to acetalic carbon. Do I have that one yet in my product?
No.
No? So what could I do? Whoops, not use an eraser. Bond to an oxygen. Right? End result, where did it end up? Next step goes to OH, and then it becomes the carbonyl, right? Done. Carbonyl. Water is made up of what? H2O. If we look at the carbon structure, what was added to the carbon structure? Not the big problem. Keep it simple. Did I add any hydrogen to my carbon structure? Nope. I broke 2 oxygen bonds and I made 2 new oxygen bonds. What happened to the hydrogens? It's H2O. Where did those 2 hydrogens go?
Going both in the
Onto the ORs, the alcohols that were busted off. Those shouldn't be negative, they should be neutral. They're neutral because what did you attach to them? H+. So what does that mean we need to do to finish our structure?
H's need to be on the O.
Add H's. And what do you now have?
Beautiful structure.
Beautiful. That's a stretch. But you now have your answer. fit to the pattern behind it. I don't know how to draw it. You don't need to make it look pretty. You just need to draw the answer. The only thing that changed was the two bonds between the oxygen and our anomeric officially carbon. Delete them because they weren't in our final product. Right? Our final product should have a carbonyl. That's coming from water. So, draw the carbonyl. We deleted those bonds. To make a final product, we'd have to neutralize them. We could address that those are coming from the hydrogens from our water. And we now have our final structure. Fun thing about this one is if you saw this on an exam, do you think it would look like this? No? Why not? You want to say the mean answer? You can say the mean answer. Okay, you can say it looks bad. This is a very high energy drawing. You have effectively all of those structures, all those bonds cis to each other, circled up on each other. That's very high energy. Should you ever be drawing a high energy product? No, so what should you do?
Draw it out again.
You should redraw this so that it's low energy. The low energy structure is what's going to show up on the exam. That would be one of the multiple choice. Because you're responsible for making those manipulations. Right? One of the things that you will probably note will happen is you'll see a couple different answers with carbonyls and alcohols connected to them. But I would bet one is a ketone. Why a ketone? Because when you looked at this, you recognized and said, oh, it has to be a ketone. It doesn't have to be a ketone, it has to be a polar pi bond. So depending on what you've memorized, you can shaft yourself. Right? The next part is you'll probably see varying amounts of carbons within the chain. Where this 2-carbon thing, that branching is, will shift to different positions. Why? Because when you unfold that structure, are you able to keep track of where all those pieces are? Right? Probably not. Okay. Probably not means you don't deserve credit because you don't understand that unfolding part, and that's why that answer choice is there. So pay attention to how you unfold things. You're responsible for that content. Okay? The location of where those 2 carbon, where that branch point is, that's going to be a location thing, but what you could do is zero in relative to something. Right? If that's my carbonyl carbon, how do I know that's going to be my carbonyl carbon? That's connected to the 2 oxygens. From my carbonyl carbon, 1, 2. That's where my branch is. I don't need to draw that necessarily. I can use the multiple choice and leverage what I know about where those systems are. Right? The other thing I can do is if I drew it all out, and this is going to happen increasingly with everybody's homework, is it'll be very easy to add or lose a carbon. Okay, so particularly when it comes to smart work, enter your answer. If it kicks back and says you're wrong, your very next thing should be to count the carbons that you were given to start with and count the carbons that you drew in your answer. If they match, now you can move on to larger content things. If they don't match, you either added or removed a carbon. You should figure that out first because that's probably the simplest, easiest answer. And again, that is a very common thing to see in multiple choice, is we either add an extra carbon or we remove an extra carbon, and students tend to fall into that trap swiftly. Make sense? And I need to be done.
The oxygens